This is a video about a little challenge I've set myself, which is to get some decent motion control using the cheap brushless motor controllers that you can buy off of eBay. Now there's two types. There's without Hall effect sensing, which is the simple one you're seeing here, which has got basically a direction and a voltage for the speed coming in and the outputs for the motors. Look at the construction there, you can see it's fairly cheap. And then the other type that's available has got the Hall effect coming in from the motors. So if you look at the left hand side here, you see the same kind of control, which is voltage and direction, and the Hall effect there, which gives it a better judgment of where the motor is, so you get more control with the Hall effect. Now I've connected it to two types of motors. In the rear there's no Hall effect, which is connected to a standard sort of brushless motor you'd find in a model car or a model plane. It's 770. And the first problem here you can see is there's barely any torque at the low and silent speeds that you'd like to use a brushless motor at. Taking it up a little bit more, there is a bit more torque. You can see this thing's pulling about 30 odd watts when we stop it, and you can see that the controller validly switches off the power when it knows the motor's stalled, which is quite useful. Now I'm going to run it up through its full range, and the problem here is the waveform that it's delivering to the motor is not that clean, which is making the motor make this noise, and it's going to cog at some point and you'll actually hear it stop where it just can't deliver anymore. And there you go, that's where it's sort of run out of sync. So we're going to run it at a normal speed now and just keep tapping the reverse button, and you can see that it slows down and there's a little dead spot before it goes back the other way, which means for the kind of motion control that I want to do, which is, you know, either moving a dolly or moving a pan or a tilt or something like this, it means it's not going to smoothly go from forward to reverse, so that's not particularly useful. Now this is the one with the Hall effect, and it's driving a skateboard motor. Again, at very low speeds, which is dolly sort of speeds, you can see that there's barely any torque. Now when we take the voltage up a little bit, you'll see that there's a lot more torque. In fact, I have to hold on fairly well. You'll actually see the table shake, which is, it's just a Black & Decker workmate that this thing's on, but you can see that thing's pulling quite hard. Next thing I'm going to do is run it up through its range, and you'll see that this thing runs pretty quick. I guess that's because a skateboard can do about 20 miles an hour, so I can't ever imagine a camera dolly wanting to do 20 miles an hour. I suppose I could do. I suppose we could have one that was chasing somebody, then the noise wouldn't be quite so bad. But the power on this thing is really quite good. Next thing I'm going to do is do that reversing test again, and you'll see that it behaves roughly the same as last time. So there it is, spinning at a reasonable speed. We hit the reverse button, it stops, goes back the other way. Hit the reverse button, stops, goes back the other way. And it looks to me that the deadband between the two is not quite so bad. Anyway, I think for the job that I want to do, we're probably going to have to look at stepper motors and trinamic drivers.